Okie dokie, chemists, let's get started. All right, this is our last week of lecture. We have a little bit more of chapter 21 to finish up, but it's a short, fun, and explosive chapter. So we'll just take our time and we'll do a little bit of review at the end of class. Same thing for tomorrow, on Thursday. But a couple of announcements before we get started. Rev F. First, where's my pen? There is a lab survey that was posted last week by the lab supervisor. This lab survey is 30 points. It is a line item in your lab grade book. So completing it will give you a nice 30 out of 30, full assignment buffer towards your lab grade. Not completing it will put a 0 in that grade book. So this isn't extra credit, it's actually a line item. So it is in your best interest to complete that. Looking ahead for lecture, we're gonna finish all of the lecture material that's going to be on the final today. There's a little bit more to this chapter. I have a couple homework questions on nuclear energy, and so we'll just spend the first 15 minutes of class talking about that on Thursday, but that material's not on the final. I have that clearly marked where that material ends. With that in mind, since we will finish chapter 21 this week, that last homework set for chapter 21 will be due on Monday at midnight. According to the syllabus, we've always had a late homework policy in place for any individual unanswered questions from online homework. Any unanswered questions, individual ones can still be submitted late for partial credit. Completing incomplete homework questions can only improve your grade. It can only improve it. So it is in your best interest to submit all questions by the end of the term, but I have that due date, and the cutoff for that is Tuesday reading day at midnight. That's the last day for you to submit any online homework for credit, including all of the late work. So basically your access to online homework is going to end on Tuesday at midnight before final exams starts. And so keep that in mind, that you won't have access to online homework during finals week to study, but in general you probably shouldn't be studying using online homework. You should be using the practice resources that are more similar to the exam instead, but do keep that in mind. And speaking of the final, I didn't write this, but I have all of my final exam resources posted, so I posted that as soon as the last group took midterm 4. I don't know if you noticed, but yeah, all of my final exam resources are posted. It's basically just like a hodgepodge of chapter 20 and 21 questions, plus some cumulative questions as well. My final exam resources aren't as well developed as my midterm exams, but do recognize that you have all of the previous resource pages to help you there. So on the final exam resource page, I have all of the practice midterms from previous in the term. And then finally, I do plan on doing a final exam review session on reading day on Tuesday, April 23rd at 10 a.m. In this room on Zoom. I haven't posted that information yet because I just decided this like an hour ago that I'd do it. So I didn't even book the room yet. So I'll post information about that when it exists. And then finally, I'll ask kindly that everyone sign the wood block that is making its way along the classroom. Where's the wood block? Who's holding it? Who has the wood block? Yeah, okay, so the wood block is over here. So this is a small thing that I've decided to do every year, a tradition, where I have students sign this big wood block that says 1220 on it. So there's a Sharpie with it. You can go ahead and leave a piece of yourself with me before you leave to go on to organic or whatever. But that wood block is there for you to sign to, you can write a note or whatever. Remember, there's 2 sides to it too. If you'd like to leave a piece of yourself with me before you move on. And so the story behind that wood block and why it's wood is, I don't know if you've ever noticed that I always bring a block of wood to class. This piece of wood is iconic. Actually, this is not my original piece of wood. I lost mine. I think someone stole it. So if you see a small piece, I had to find another piece of wood to bring to class to elevate my iPad because I like to be ergonomic, but I'm also cheap. I don't want to buy something. I don't want to buy an iPad stand to prop up my iPad, so I just use like a piece of trash, essentially, to do that. And so in previous years, every year students ask me about it, what's that block of wood? And I tell them the story, and it's become iconic, and students are like, oh, can we sign the piece of wood at the end of the year, you know? And I thought that was a good idea, but I like my piece of wood, so I just have a different one for you. For each class. So I have like almost 10 of these now over the years I've been teaching. I'm hoping that with enough time, I collect enough blocks of wood that I can build myself a new office because my office is really bad. But you know, in 10 years time, if you come visit me, you can come find your name on the block of wood and I'll always have a piece of you. So I'll bring this block of wood to office hours, to the review sessions, to the exam, the final exam. So as long as you're interacting with me, you can find me with the block of wood to sign it during this last week of classes. All right, so block of wood, sign it. Good, all right, announcements. Okay, so now let's continue on with nuclear chemistry. Let me just remind you what we've been talking about. We've been talking about 3 common types of radiation: alpha, beta, gamma rays. We talked about their energy and how they interact with our bodies based upon their mass and energetics. So we talked about alpha particles, beta, and gamma. All 3 of these radiations have enough energy to ionize water. Where this becomes a big issue is if we get these radiations inside of our body. All right, where, you know, we talked about smoke detectors. They are an alpha emitter. Americium 241 is an alpha emitter, but it's on our ceiling, encased in plastic and metal. So we are shielded from the majority of those alpha particles when it's affixed to the ceiling. So that's why we're not super worried about the alpha emitter in our smoke detector. But we contrasted that to radium girls in this story where these women were dipping their paintbrushes in their mouth. They would lick the tip of their paintbrush that had a little bit of radium, an alpha emitter, in it. And so once they were ingesting that alpha emitter, it was like a grenade going off in their body. Now those alpha particles were ionizing the water inside their body, and that's what makes the big difference between our smoke detector alpha emitter and the alpha emitter in radium girls. There's also another issue that I forgot about is, you know, we live in Ohio, the Rust Belt. We have hard water, and a big concern of ours is radon in our basements. So you might be nodding along like, yes, that's a big concern, and a lot of the homes in this area have a high amount of radon that leaches out from basements, like uncovered basements. And so radon gas, which is also an alpha emitter, can accumulate in a basement. And so why it's so dangerous, radon gas, is because radon is an radon is an alpha emitter, but it's also a gas. So oftentimes what happens is we can breathe in that gas, and then the alpha particles from that radon can you know, do its disintegration thing, and then it can be really bad. So radon poses an extra concern because of it's in that gas form. So much like radium girls, where it can come in contact with our bodies. All right, so those were the 3 more common radiation types. So we'll talk about 2 other ones that are less common, but you know, our strategy is the same, to use the mass numbers and number of protons on each side of our reaction and keep everything balanced. We can ignore overall electron charge for the most part. We're just looking at mass number and atomic number when we balance things. So our last 2 less common decay processes actually net the same result, but they're just a little bit different. So notice the language that's used here. So the first one is positron emission. So emission means that this positron, this thing, is a product. So that's half the battle, putting your particle on the right side. A positron is like the opposite of an electron or a beta particle. You can think of it that way. A positron has 0 mass, but a +1 charge, versus if you remember, a beta particle has 0 mass but a -1 charge. So you can think of a positron as the opposite of a beta particle. And so, and it behaves kind of oppositely here, where if a proton emits a positron, that proton is converted to a neutron. So you can see that reaction here. A proton is our reactant. If it emits a positron, there is my positron product. And then you ask yourself, ask yourself, what's the missing piece here to make everything charged balanced? I need my other product to have a mass number of 1 and a atomic number of 0. So I don't know about you, but something with a 0 charge and a 1 mass, that is a neutron. So here we just proved that when a proton emits a positron, it's basically like getting rid of its positive charge and just becoming charge neutral. And so we see here that that proton is converted to a neutron. And so within a actual chemical or nuclear reaction, here I'm telling you, potassium-40 is a positron emitter. So again, notice the language. Positron is the subatomic particle. Emitter means it's a product. So you can kind of write out your skeleton balanced equation where potassium-40 is my reactant. The positron is the product. Just locate and identify that missing piece. How many, what's the mass number of that missing piece? 40, and then how many, what's the atomic number? 18, yes. And so you look at the periodic table and you go, oh, okay, that's argon. All right, so when potassium-40 emits a positron, it is converted to an argon atom. Great. Okay, so notice the language here for this next one, electron capture. We know that an electron has 0 mass and a -1 charge, but it's a little bit different here because the electron is being captured. That electron is actually a reactant. So this is the one of the, I guess, 5 radiation sources we've been talking about that's different. This electron is actually a reactant. Your other reactant, your substance, is capturing or reacting with an electron. So what we see here is that a proton can also capture this electron, converting it into a neutron. So here you see that here is the electron that's being captured. Notice it's a reactant. But when we add up all of those mass numbers, we see that the resulting product has a mass number of 1, and then 1 minus 1 is 0. So yes, this is in fact a neutron as well. Just like in our previous example, but the decay pathway is a little bit different. Right? And so we see that when a proton captures an electron, it's converted to a neutron. So we can write an overall balanced reaction here. If potassium-40 undergoes electron capture, one of the electrons is going to be the reactant because it's electron capture, so reactant. And then you add everything up and you see, okay, my product has to have a mass number of 40 and a atomic number of 18. Look, that is argon as well. So notice that positron emission and electron capture, they both yield the same net results. It's just kind of the process is different. In one of them, you're getting rid of a positron's a product, but in electron capture, the proton is absorbing a surrounding electron instead into the nucleus. But our net result is the same. Okay. And so we'll be using these different decay modes and predicting what happens, what elements undergo what pathways in a minute. Okay, so this slide just summarizes all of the different decay modes that you need to memorize. Here on the right side, it says how the mass and atomic numbers change during a process, but I don't think it's necessary to memorize these. As long as you know your balanced reaction needs to stay mass and atomic number balanced. And as long as you know what the identity of each of your radiation sources are, then you're fine. As long as you can balance, like understanding that an alpha particle is a product during alpha emission, you can balance it to make sure that you account for the mass number of 4 and the 2 protons. So it's not really necessary to memorize the changes as long as you know what those masses are for our particles here and whether they appear on the products or reactant side. So we see for the first 4 different radiation types, alpha, beta, gamma, positron, notice how these 4 are all products. The particle is a product, but for the one weird one, for electron capture, it is a reactant. All right, reactant. Okay, so for all of these different radioactive decay modes, our identity of our elements are changing. And so that's why I mentioned before, like finally in this chapter, we are creating new substances, turning one element to another one via these radioactive decay modes. We're actually creating new elements. Unlike chemical reactions, we're just rearranging the atoms. So let's look at some examples of radioactive materials. Okay, and I got a Geiger counter here to measure the different extent of alpha emission of some of these elements. So, like I said, the elements that we see in nature, we see because they're stable. But there's a small fraction of isotopes of the elements that we interact with on an everyday basis that are radioactive, though just a little bit. Some substances are more radioactive than others, have more radioactive isotopes, and we'll look at why in a little bit. So I have 3 different samples here. I have sodium chloride. If you look at chloride, chloride has a very non-integer molar mass, meaning it's like, what, it's like 35.45, is that right? It's molar mass? Yeah, so that means that there's lots of different weights of isotopes present in a chlorine sample. So some of those isotopes are radioactive, so we can see, whoops, okay, here's my Geiger counter. I have to learn how to be quiet so you can hear the beep. So this is a sodium chloride sample. Go. Okay, so you can hear it beep like a little bit, right? It beeps a little bit. It's just a little bit radioactive. That not that many alpha particles are being emitted, but still a small amount. So that's sodium chloride. This is stuff we just, we buy on the shelf at Kroger. There is a little bit of radioactivity here. So what I have next is sodium iodide. Iodide is also a halogen, but much larger. Typically what we see is larger atoms tend to have more radioactive isotopes. So here's a sodium iodide sample. It's supposed to be more radioactive, but sometimes it's not. Sometimes it's hard to get it to do it. Okay, so this one I don't know, may tell that is beeping a little bit more than our sodium chloride sample here. Okay, see, there we go. I'm kind of like forcing it too. Because that iodide just has isotopes that are more radioactive than typical. And then lastly, I have a uranium compound. It doesn't matter what, but the important thing is that this sample does contain uranium. All right, and so we'll see the difference here. Yes, so that's very beepy, right? So these samples of uranium, much, much heavier elements, they are emitting a lot more alpha particles than our other 2 samples that we may interact with more on an everyday basis. But I mean, I feel fairly safe in front of these samples. We know that alpha particles are blocked by most things, and so as long as I'm not holding these in my hands all day, those alpha particles aren't going to cause me that much harm. But people who do maybe work with radioactive substances all day might want to have something like a lead shield that protects them much more from those alpha particles, especially if they're interacting with it every day. I only interact with this vial, I guess, twice a day, once a year. And so I'm not that scared. But for someone who works with radioactive things all the time, I want to show you that this lead shield can block that radiation. So notice how much beeping it is without the lead shield, but with the lead shield, much less. All right, so I'm literally blocking those alpha particles. All right, there we go. Yep. So there we go. So there are radioactive substances. I got, like the question is, you know, like when you go to the dentist's office and you get your x-rays done and they put the lead vest on you, and you know, those dental hygienists, they always have to calm children down and say like, oh, don't worry, like the x-rays, they're not dangerous. But as soon as they set up the device and you're grinning there with the really, those sharp pointy things in your mouth, they leave the room, right? If it were that dangerous, if it wasn't dangerous, why are they leaving the room, right? But the thing is that they are doing, what, 10, 12 x-rays a day, all right? And so it's not just, oh, it's dangerous. There's an element of like toxicity and exposure. And so these dental hygienists who are doing multiple x-rays a day, yes, that in very small quantities, that amount of radiation is not going to be that harmful for you, especially if we're only doing a x-ray once a year. But for a dental hygienist who's doing multiple of them a day, they want to limit their exposure. So that's why they leave the room or maybe put on their own lead vest so they're not exposing themselves more than they have to. All right. So there we go, radioactive stuff. Okay, so let's put this all together and answer why we see certain stable things over other things. So here are some rules of nuclear stability. Why are some nuclei more stable than others? And what we'll talk about here is how to predict how an unstable nuclei decomposes. So the first rule for nuclear stability is that anything heavier than bismuth is unstable. So that includes uranium. If you look at where uranium is on the periodic table, it's element 92. Bismuth is 83. Basically, having 83 protons in your nucleus is the most stable you can get. Once you put that 84th proton on there, your atom becomes unstable and it will decompose into something else until it does become stable. So bismuth is the largest stable element on our periodic table. If you look really closely, look at the molar masses, all right? So look at lead, bismuth. Notice how the molar masses have decimal places, but as soon as you get to element 84, what is that? Or polonium. See how now it's in brackets, 209? What that means is that polonium doesn't exist long enough for us to actually measure an accurate molar mass, so it's just an estimate because it doesn't exist long enough. So everything heavier than 84 protons is going to not be stable and always decompose into something else. Okay. The next thing is that there seems to be this special number of protons or neutrons in our nucleus that tend to be more stable than others. They call these magic numbers. I don't like the word magic because in chemistry and the sciences, everything can be explained via thermodynamics. Magic makes it sound like it's unexplainable. But here, the observation is that elements that have either 2, 8, 20, 28, 50, or 82 protons or neutrons in their nucleus tend to just be extra stable, all right? We see those numbers of subatomic particles show up often. And I think that's why they call it magic. But I truly think the reason that those numbers are magic and tend to have an extra element of stability is because of packing. When your subatomic particles pack in a nucleus, basically if they can pack efficiently, then that nucleus is going to be relatively stable. I think some work has been done is that actually completely spherical nuclei aren't the most stable. It's actually football-shaped ones that are more stable. Interesting. And so maybe with 20 protons and 20 neutrons in your nucleus, you can get a nice football-shaped nucleus. So there is, I believe, some reasoning behind these numbers, how that your subatomic particles pack within that space. And so looking at these numbers, it just seems that seeing these numbers in your subatomic particle count tend to have elements with higher stability. So here are some examples. Helium-4 has 2 protons and 2 neutrons. Remember that both of these numbers have to add up to your mass number. How to read those isotopic symbols. And so yes, helium-4 is doubly magic because there's 2 neutrons and 2 protons. When it shows up in both spots, it's extra stable. Actually, I think all of these are doubly stable. So oxygen 16 has 8 and 8 protons and neutrons. So yes, 8 is also a magic number, so it's extra stable. Calcium 20, 20, and then lead, I think, has 82 protons, because it's given there, it's on the periodic table. And then 208 minus 82, I think, is 126. So all 4 of these examples are, I guess, doubly magic. Doubly. Or doubly stable, because they have nice, good numbers for both the number of protons and neutrons. All right, and so what you notice with these magic numbers is that they're all even numbers. Just like in nature. Nature likes even numbers, okay? If you don't believe me, think about when you increase the volume on your TV. Are you the type of person that has to end on an even number? Why? Do you have to? No, but you just want to, because nature pulls you in that direction. That there's more, I guess, stability, more satisfaction when you end on a positive number, or a even number. Nature is like that too, where you are more likely to run into isotopes with an even number of subatomic particles rather than an odd number, and it's quite obvious here. All right, so you see here that elements with even number of protons tend to have more isotopes than odd number, elements with an odd number of protons. That's weird, that's just weird, right? Also, here, I think this table really highlights it. Of all of the isotopes on the periodic table, remember, each element may have 1, 2, 3 different isotopes. There are 158 isotopes that have both an even number of protons and neutrons, both even. But you look at the number of stable isotopes that have an odd number of protons and an odd number of neutrons, there are only 5. Isn't that crazy? So yeah, just like humans, nature tends to like even numbers as well. And so that just aids to stability. We're not going to look into the reasoning here. It's just an observation that we see. Okay, so let's talk about how we can predict the stability of isotopes and predict how does it have to decompose if we have an unstable isotope. So if it's unstable, how will that sample decompose to become stable? So a lot of our stability actually relates to a neutron to proton ratio. So basically the contents of your nucleus is what determines is it stable or not. And so just like in these previous graphs, oftentimes what we see is we look at the observations first and make some type of trend or correlation. So what we see for many light elements, so look at this graph, look at very light elements like oxygen, nitrogen, hydrogen. In your nucleus, what's most stable and what's most seen is a neutron to proton ratio of 1 to 1. All right, so for light elements, we typically want a 1 to 1 ratio of neutrons, so the neutral one to protons, the positive one. But as we get heavier and heavier, heavier elements, so let's say iodide up here has a optimum neutron to proton ratio of 1.4, so a little bit more neutrons than there are protons. But for light elements, a 1-to-1 ratio is typically preferred. And so using this trend, understanding that, okay, around 1 is preferred, depending on the composition of an actual unstable isotope, we can predict what mode of decomposition is going to happen. So there's 3 different possibilities that can happen for nuclear decomposition. Let's do the easy one first, and that's actually the third one. All right? So the third one is for any isotope that's heavier than bismuth. All of those isotopes will undergo alpha emission. So just memorize that. We'll always go alpha emission. So if I ask you, what does uranium like 238 undergo, you will say alpha emission because it's heavier than bismuth, right? But now the other 2 methods that we use to predict what type of emission is going to happen depends on its value of its neutron to proton ratio. So you have to calculate it first. So here are the 2 options. You can either be above the belt of stability, so all these blue lines are stable isotopes. So you might be given an isotope and it's above the belt, or it's below the belt. If you're above the belt of stability, you want to move down the belt so you get closer to the blue region. But if you're below the belt of stability, you want to increase your neutron to proton ratio to get you closer to the blue region there of all the stable isotopes. So this is what your options are. If your neutron to proton ratio is above the belt, so well above 1, what I want to say is like well above a neutron to proton ratio of 1, you're most likely going to encounter beta emission. And the reason is that beta emission converts a neutron to a proton. So how your neutron to proton ratio changes is if a neutron is converted to a proton, your numerator decreases, but your denominator increases. And so what that happens is your total neutron to proton ratio decreases. So you were like high on the neutron to proton ratio belt, but then doing beta emission brings it down closer to a more reasonable number, closer to 1. All right? So that's if you are above the neutron to proton ratio. Versus if you're below. So I'm going to say, yeah, like I'm going to say below 1. But 1 is a approximate number. 1 is typically what we have for light elements. As elements get heavier and heavier and heavier, the optimum number is actually above 1. And we'll look at some examples in a moment. And so the reason that if we are below the belt of stability, our goal is, okay, let's bring up that neutron to proton ratio to get you closer to the belt of stability. So to do that, what we do is electron capture or positron emission. Both of these net the same thing, but basically what happens is that a proton is converted to a neutron. So what happens is that the numerator gets larger because we've made a neutron, but we've consumed a proton, so the denominator gets smaller. So in general, your entire neutron to proton ratio increases. So if we were below the belt, converting a proton to a neutron increases your neutron to proton ratio. All right? So those are what you need to remember. If you have a high N to P ratio, beta. If you have a low N to P ratio, positron emission. All right? That's how you get closer to the belt. And then finally, for heavy isotopes, ones that have tons of protons, you can think, okay, if you have tons of protons, you're over here on the belt of stability, like way high on a high number of protons. In order to get closer to the belt of stability, you actually want to move diagonally, closer to where these blue lines are. You want to decrease your number of protons as much as possible to get less than 82 protons in your nucleus. And so the reason that alpha emission occurs is because you subtract both protons and neutrons. So your N to P ratio actually moves diagonally. So when you calculate this, it's N minus 2, P minus 2, and this is how you move diagonally across that belt of stability the most. Right, so it's all about getting closer to those blue dots, and the different emission types helps you do that. So definitely just, I guess this is very flashcardable of what types of N to P ratios yield different processes. So how will they be asked on an exam? So let me point out, on an exam, I'm 99% sure you will be not given this table. So you need to be able to answer these without the table. But here's the thing, for the most part, it's obvious if your ratio is too high or too low. You don't need the chart, okay? It's usually quite obvious if you recognize that 1 is usually preferred for relatively light elements. So let's go through these. I want you to tell me what is the predicted decay mode for the decay of these different elements. So our strategy is calculate the N to P ratio and relate that ratio to the belt of stability. That should relate to a certain emission type. So carbon-14. Carbon-14 has how many protons? 6. Yes, that comes from the periodic table. 14 is the mass number, remember? So does that mean there's 14 neutrons? No, there are only 8 neutrons because the number of protons and the neutrons, that missing piece, add up to that mass number. Just reviewing. Right, and so these are the numbers we need to calculate the N to P ratio. So 8 over 6, I think, is 1.33. So tell me, are we above or below or on the belt of stability? Above, well above. Do we need the graph to tell that carbon-14 is above? No, you don't need no graph, right? You're well above 1. So this is way too high. So just go back a slide. Tell me if we're above the belt of stability, what decay mode is probably going to happen? Beta. Yes, beta. Let's prove it to ourselves that making a beta or emitting a beta particle makes a more stable element. So let's take carbon 14. So carbon has 14 mass number, 6 protons. If a beta particle is emitted, it's the product. So beta is the product. What are the numbers for the missing piece? What's the mass number of that missing piece? 14 and 7. So what is that? A nitrogen atom. So this nitrogen atom has 7 protons. 7 protons, and then how many neutrons? Also 7. So what is its N to P ratio? 1. Is that good? Yes. So if carbon 14 undergoes beta emission, it makes a really stable nitrogen 14 atom, which is the most abundant nitrogen that's there. All right. And so we did that beta emission. That's why we say, oh, it lowers your N to P ratio. But that just proves that what we did was good. It was more stable when carbon 14 undergoes beta emission. Okay, next one, calcium. So same idea. Get the number of protons. What is that, 20, I think? 20, yeah. So therefore, 18 neutrons. So its N to P ratio is going to be 18 over 20. Oof, it's going to be 0.1, or sorry, 0.9. So this is way too what? Low. It's way too low. So what decay mode is probably going to happen? Positron. Positron emission, or electron capture, it both does the same thing, right? Positron emission. And then you could prove it to yourself. You could predict what is the new product, and you'll get a N to P ratio that's closer to 1. And then the final one, uranium. So uranium is element 92. I think if you do the subtraction, there are 239 minus 92, 147 neutrons. Do I even need to calculate the neutron to proton ratio here? No. So what does this element undergo? Alpha. It does alpha emission because it is a heavy element emission, because its number of protons is greater than 83. All right, that it's heavier than bismuth. Anything heavier than bismuth always undergoes alpha emission to get it closer to bismuth, to try to make that nucleus stable at all. So uranium just has too many protons, so it's going to undergo alpha. Okay, so you don't even need the neutron to proton ratio there. Okay, so how can we word exam questions? So we could easily word an exam question like this. I could just simply say, calcium 38 will most likely undergo which decay process? And I'll give you the options, beta, I'll give you beta, positron emission, alpha emission, and then just like some weird distractor, all right? And there's a multiple choice question. So recognize you need to calculate the N to P ratio and see, are we above or below that belt of stability? Or I can ask it this way, where I'm forcing you to calculate it 3 times, because here I'm asking which of the following is most likely to decay by positron emission. So I hope in your mind you recognize, okay, positron emission means we are looking for a N to P ratio that is very low. That's what we're looking for. So we have to calculate it 3 times and pick the one that's probably the lowest N to P ratio, because that's the one that will benefit the most from positron emission, because that raises that ratio. So here's just another way. It's still assessing the same thing, just asked a little bit different. So chromium, I wrote this down, has protons. It has 24 protons, manganese 25, iron 26. So if you do the subtraction with the mass number, you can get the number of neutrons. So chromium has 29 neutrons, manganese has 26, and iron has 33. So if you calculate the N to P ratio for all of these, chromium is 1.22, manganese is 1.04, and iron is 1.27. So of these 3, which one is most likely to undergo positron emission? The manganese one, yes, because its N to P is the lowest. But you might be thinking, but it's over 1. But remember, it's only for light elements a 1-to-1 ratio is preferred. As the elements get heavier and heavier, the optimum N to P ratio increases. But this question is just asking which one's most likely. So positron emission typically happens with low N to P ratio. So the lowest one is probably going to be our answer here, since it is the lowest, even though it's above 1. Like, it's not obviously low like calcium was, but it's still the lowest. Okay, great. All right, so that's definitely a learning objective within this section, is using the belt of stability, though I promise you probably won't be given it, to predict what decay mode happens. I can guarantee that. And then the last one that's kind of new, but not really, is using, looking at a radioactive series. So in all of our previous work, I would just say, okay, 1 alpha emission happens, or 1 beta emission happens, or gamma emission happens. But for the most part, a lot of the nuclear elements that we work with actually don't decompose in just one step. They have to decompose in multiple steps in order to finally become stable. So an example is uranium-238. So uranium-238, whether it's used in nuclear weapons or nuclear power plants, actually decomposes by a series of alpha and beta emissions, all one after one another, until it becomes a very stable lead compound. So right here, uranium has way too many protons, but once it becomes this final lead compound, it finally is stable and it stays there for much longer. So the learning objective from this part of the book is not, oh, memorize the series. No, it's if I tell you a starting point and what nuclear decays happen, can you predict the product? So it's essentially, can you do 4 nuclear equations all in a row? That's essentially it. But remember, it's still all about just balancing mass numbers and atomic numbers. That's all it is. It's just you have to do 4 of them all next to one another. So our strategy here is, okay, uranium-238 undergoes alpha emission. An alpha particle is 4 mass number and 2 protons. So when that alpha particle is emitted, it is a product. So we need to think, what is the missing piece that has to balance that decomposition of uranium? So it's going to help us if we put that uranium has 92 protons. So we see that that missing piece has to have 234 mass number and 90 protons. Right, that is if an alpha particle is emitted. But typically what I like to do is put the alpha particle up top here, recognizing that, oh, that alpha particle is emitted, that these are my 2 products. When we add them together, have to equal that 1 reactant. All right, and so we can identify this element as thorium if you wanted to, but we actually don't really need that for the next step, because we're just going to go straight on and do the next disintegration, which is a beta particle. So a lot of this is just memorizing those numbers for the different radiation types. So a beta particle has a -1 charge, but -1 charge, but no mass. So again, this beta particle is a product. So ask yourself, what is the missing piece to make everything balanced? So the mass number doesn't change, so it stays 234. But how many protons now? 91, yes, 91. And you look at your nifty periodic table, and then it's PA. So that is when a beta particle is emitted. Then we do another beta particle, because that's what the series is telling me to do. It's saying to do an alpha, 2 betas, and then an alpha. So we see here, when another beta particle is emitted, it's 234, but then our mass number goes up, or no, mass number doesn't change. Number of protons goes up to 92 now. And so what is that? Uranium. Weird. We started with uranium and we came back to uranium. That's weird. But let's note that the mass numbers are different, and that's the big difference. The big difference here. All right? And so when this uranium, oh, it's not UR, it's just U, we're doing our last and 4th decay, which will be an alpha particle. Remember, this alpha is a product. So that alpha particle plus the product I'm predicting, so 230 and 90, has to add up to that reactant. So 90 is back to thorium. And so that is the resulting nucleotide, or so the resulting nucleus after these 4 decay. So it's just 4 of them in a row. That's it. Okay? Same work as before in balancing our mass numbers and atomic numbers. We can just ignore charge. Right. The actual series and order of things is not important, but this is how uranium goes from a radioactive substance used in nuclear power plants all the way to lead, where it no longer is actively radioactive. Yeah, there's multiple steps here. Okay. All right, and then the last kind of equation balancing before we jump into what is actually review is nuclear transmutations. So in all of the other examples of balancing nuclear equations, we were always emitting like beta or alpha or something. Those particles, the radiation sources, were always involved. But with atom smashing or nuclear transmutations, we're actually smashing atoms together to make new atoms. All right, we're still conserving mass number and atomic number. It's just we're working with larger atoms in general, that these things aren't decomposing. We're actually forcing these atoms together. And so we actually do this in the Large Hadron Collider in Europe. It's a particle accelerator, or an atom. You can think of it as an atom smasher, where we have these big circular tracks that allow us to take a neon atom and like spin it around. And then in another track, we can put that alpha particle in another track, spin it around, so it increases its kinetic energy and velocity to the certain point where we bring the two together and smash them together with a high amount of energy. So that's why we call it an atom smasher. So here, how we balance the equations are basically the same. We need to make sure those mass numbers stay consistent. So in this first one, I am smashing together a neon and an alpha particle. So what I like to do is just take inventory of both sides. The mass number adds up to 24, while the number of protons adds up to 12. So I need the same thing on the product side. So the oxygen that I already gave you here is some of the mass. So the missing piece has to have a mass number of 8 and 4 protons. And so if you look at the periodic table, that is a beryllium atom. And so if you add up your product side, mass number and protons, it should still add up to your reactant side as well. So I hope that all looks familiar, right? It's just we're utilizing it a little bit differently because we're smashing atoms together. Things aren't just decomposing on their own. All right. So let's do this next one. Same idea. Here we're smashing together 2 neon atoms. And so we just add up the 2 sides, the 2 reactants, add up to a 40 mass number and a 20 number of protons. And so we want to make sure that our product side add up to the same thing. So our product, we have oxygen, we have something, and then we have something else. What is that symbol at the end there? That's gamma. Do you remember the weights and stuff for that? 0 and 0. So is it actually going to affect anything? Nope, not going to affect any of our balancing. I'm just trying to communicate, you do this, and a butt ton of energy comes off too. And so our missing piece is 24. I don't know. That sounds right. And 12. And so that is a what? Magnesium. Perfect. So we are taking, what's neat, look, we're taking 2 neons, and we're getting an oxygen and a magnesium out. That's kind of cool, all right? It's kind of like, not like magic, but yes, we are in fact creating new elements from other elements. But it takes a butt ton of energy to do that, to run these particle accelerators here. Okay, so hopefully that was kind of review. All right, so let's do the very last part of the chapter. The last part that's on the exam, so I'm just going to reiterate that the first 4 sections of this chapter are on the exam. So the last one we're about to cover right now, and that's rates of radioactive decay. But here's the thing, you already know how to do everything here, right? It's just chemical kinetics, that's it. So you already know how to do it all, so it's really just review. And then the last 3 sections is just going to be for fun. You have some homework questions on it, but it's not on the exam. I'm going to spend like the first 15 minutes on Thursday talking about bombs, but then we'll just do review. So I won't spend too much time on it, but you do have homework questions on it. Okay, so let's review. Rates, chapter 14. So how fast do radioactive decay processes happen? Well, all radioactive decay processes follow first order kinetics. Yay! So that means we get to use the first order integrated rate law. So if you know how to use this equation, then you know how to do radioactive decay, right? But remember, so our integrated rate law relates the concentration after some time versus what we start with minus the rate constant times how much time has elapsed. So that rate constant is really important. That's the same rate constant as in our rate law. Rate equals K, you know, concentration of stuff, right? It's the same K from our rate law. So that K is important. But the thing is for most radioactive decay processes, we don't report how fast decay happens in a unit of K. We usually report it in terms of half-life instead, because half-life makes more sense to us, you know? We understand the context of half-life. And so the half-life, I don't want to say it's a half-life calculation, because this half-life, this equation, T1 half equals, this is the same as natural log of 2 over K, is just another way to represent rate constant. You don't actually plug in any like times or amounts or concentrations in here. This just allows you to make rate constant like a better number that you can understand. That's it. It just converts the T1 half to the rate constant. You're not actually using it to calculate anything other than just represent the rate constant differently. So you will be constantly using these 2 equations to interchange a rate constant to a T1 half. Because how we actually can think about how half-life works through kind of an intuition standpoint is understanding that if 1 half-life goes by, you lose half your sample. So that's where this last equation comes into play, but I'm going to warn you on this equation. It only works sometimes, but the integrated rate law always works. This only works sometimes if like the half-lives are whole numbers. So I would probably just not use this equation, just use the integrated rate law because it always works. So let me give you an example of how this equation works. Okay, pretend we have 100 grams of sample. If we undergo 1 half-life, how much sample is left? 50 grams, yes. So this was 1 half-life, we divided by 2. That's what this equation is saying, is that if we start with 100 grams, n is the number of half-lives that go by. It's basically how many times do you have to divide by 2, all right? Okay, so, but what if another half-life goes by? Then we only have 25 grams, yes. And then what if 3 half-lives go by? Then it's 12.5 grams, all right? So each time a half-life goes by, we lose half of our sample, all right? So, with that in mind, there's actually 2 ways to do this question. The easy way that only works sometimes, or the integrated rate law, which I actually think is the easy way because it always works all the time, 100% of the time. So let's do it the easy way first, the cheater way. Let's call it the cheater way. Okay, we have a radioactive substance and it has an initial mass of 48 grams. After 160 hours, 30 grams of sample is left. What is the half-life? Okay, let me show you the cheater way first. If we start with 48 grams, what if 1 half-life goes by? How much do we have left? 24. And then what if another one goes by? 12, then 6, then 3. So how many half-lives went by? 4. So 4 half-lives went by, and it took 160 hours. So what does that mean 1 half-life is? 40 hours. Okay, that's the cheater way. The only reason it works is because the numbers are really easy. But what if the numbers aren't easy? Will this work? No, it won't work. But the integrated rate law will always work. So let's do the integrated rate law and get the same exact answer, okay? Where, remember what kinetics is and using the integrated rate law is just reading comprehension, okay? We start with 48 grams, so this is A sub 0. After 160 hours, this is T. And then 3 grams left, this is A sub T. So what we're going to do is actually use the integrated rate law first. We're going to calculate K and then plug that K into T1 half. So it becomes a nicer number to look at because we have A sub T, we have A sub 0, we have how much time went by. And so we're just going to use these two equations and we'll get the same answer, I promise you. Okay, so this was the cheater way. Let's do it the real way. So natural log of what I have left over, so 3 grams equals natural log of what I started with, 48 grams, minus, I'm solving for K, 160 hours went by. All right, so I'm solving for K. So move some stuff around, and I think I have it right there, that K, when you solve for it, you get 0.0173 hours to the negative 1. So a time inverse is common for a first order reaction. But I don't know about you, that's like not a great number. I don't understand, I don't know if that number, is it fast or is it slow? I don't know. So let's convert it to a T1 half where it's a number like I can actually understand. And so we use the T1 half equation. T1 half is natural log of 2 over the K we just got. So 0.69, what is it? 3 over K that we just got, 0.0173, hour to the negative 1, and yeah, if you put that in your calculator, you do in fact get 40 hours. So see that you get the exact same answer, But here's the thing, you can plug in any numbers in the integrated rate law. The only reason we were able to do the cheater way is because the numbers were really easy and all divisible by 2, right? But if you have real weird wonky numbers, that integrated rate law is never going to fail you. Okay, so let's do another one. Same thing, we're going to be using the integrated rate law and the T1 half equation. Here I tell you radium has a half-life of like 1,600 years. Marie Curie isolated 0.21 grams of radium in 1902 and left it in her lab undisturbed. How many grams is left? So here I wrote this question 2 years ago. So that means it wasn't 120 years, so let's calculate it for 122 years. Sure. See if the number is that different. It's not going to be. It's going to be very similar. All right, because, yeah, in 2024 or whatever it is. Okay, so the idea here is I give you the T1 half value. I tell you the half-life of radium. So from this value, it's synonymous of giving you K. But we need to calculate K. We need to calculate it from that T1 half equation. But then once we have K, then we can plug in the missing pieces here. I know how much sample I start with. I know how much time has gone by. I know the rate constant from the T1 half. I can calculate how much I have left. So really this question is just like the previous one, but it's opposite. And the idea here is we are never plugging anything into the T1 half equation. We are only using it to interconvert between a T1 half value and a K value, a rate constant, because we need the rate constant for the integrated rate law. So K is natural log of 2 over the T1 half I was given, so like 1,600 years. So we see that the rate constant for this reaction is a number. It is 4.36 times, 10 to the negative 4 years to the negative 1. So this number isn't super useful to look at, but it is useful for the integrated rate law. Because we're going to go ahead and shove everything into that equation and solve for how much sample do I have left. I know how much I started with. I know K now. I know how much time has gone by. So I am solving for A sub T. So natural log of the junk I have left, is equal to the natural log of what I started with minus the K value I just got. Actually, let me put the numbers in. I started with 0.21 grams minus K that we just got, years, and then how many years? 122 years. All right. Putting all of that together, if I calculate everything on the right side, I get that the natural log of what I have left is equal to negative 1.61. And so if you take e to the both sides, we get that the amount of solid I have left is 0.1991 grams. So yes, our sample did disappear a little bit, okay? And it's a little bit more than, so like like a fraction of a microgram more over the course of 2 additional years. But we see that we have less mass than what we started with because some of it disappeared. It degraded into a different substance. Okay, great. All right, so we're just utilizing the first integrated rate law again and using reading comprehension like this one. A sample lost 62% of its mass in 12 hours. What is its half-life? So here, it's all about getting those variables. For this one, don't try to plug it into the, oh, you lose half your sample, whatever. It's not going to work. For this one, it's best to just use the integrated rate law, where A sub 0, what we start with, let's just say is 100%. So then how much do we have left after 12 hours? 62%? No, not 62%. If we lose 62%, we actually have 37.9% left. Yes, yeah, so it's all about reading comprehension. So we lost 62.1%. So has a full half-life gone by? Yes, but has 2 half-lives gone by? No. So it's somewhere between 1 and 2. Right? But we need to use the integrated rate law. We can't use the cheater way here because we're talking about fractions of half-lives. So don't even try to do it. Just use the integrated rate law because I tell you time, I tell you a sub 0, I tell you a sub t. So what we're going to do here is calculate K with all this information. So natural log of 37.9 equals natural log of 100 minus K. That's what we're solving for, but 12 hours have gone by. And so I think if you solve for this, you get that K is equal to 0.081 hour to the negative 1. I have no idea if that is fast or slow, so I'm going to convert that into a T1/2 so it makes more sense to my little pea brain. So natural log of 2 over 0.081 hour to the negative 1. And so converting that, you get that the T1/2 is 8.57 hours. That makes more sense to me. You lose half your sample in 8.5 hours. That I can understand. So it hopefully should make sense that you lose over half of your sample. You go from 100 to 30% in 12 hours. So those values do make sense there, right? If the numbers didn't, trend with one another, do check your work there. All right, so that is all review. Was anything there new? Nothing there was new. You should have known all of that. And so some applications of using the integrated rate law is that a lot of elements that are radioactive have known half-lives. And so what carbon-14 dating is, the concept behind it, is that all living things, you can think of all of us, our carbon atoms are in equilibrium. There's a set amount of carbon-14 in our world, and we are constantly exchanging our carbon-14 with the world. When we eat foods that contain carbon, we always have a set amount of carbon-14 in our bodies, set amount, as long as we're eating food and living. But as soon as we die, we no longer replenish the carbon-14 in our bodies. So when we have non-living things, once things die and they stop replenishing their carbon-14, then that carbon-14 just starts to decompose, and it gets less and less and less. So the idea is, if I know how much a living thing, how much carbon-14 is in a living thing, that's A sub 0. That's how much you start with. Versus if I can measure how much carbon-14 is in this object, it's less than what a living thing has. As long as I know the half-life of carbon, I can figure out how much time has gone by. It's essentially utilization of the integrated rate law. That's it. Right? Understanding that living things have less amount of carbon-14 because they're not exchanging it with the environment. Okay, so we're using the integrated rate law. The T1/2 for carbon-14, which is typically how dating happens, is almost 6,000 years. But what's more useful for us is the rate constant, K, because that's usually what we put in the integrated rate law. So K comes from the T1/2 equation when you rearrange it. K is equal to T1/2, K is equal to natural log of 2 over T1/2, which is the 5,715 years. And so you get that the rate constant is 1.213 times 10 to the negative 4 year to the negative 1. That's the K you want to use for your integrated rate law to calculate how old something is. All right? Calculate how old something is based upon how much, how much of the carbon-14 was present before the thing died, so let's say 100%, and then how much it is currently when it was measured. That's A sub t, and you're solving for how much time has gone by. All right. Let's talk about some misconceptions of carbon-14. Like, yes, you understand carbon-14 is a radioactive substance. We're measuring how much of it has gone in non-living things. But let's kind of quash a misconception. Let's recall, what is the neutron to proton ratio of carbon-14? Carbon has 6 protons, therefore it has how many neutrons? 8. So its neutron to proton ratio is 8 over 6, so 1.33. So based upon this answer, what does carbon-14 decompose into? Does it decompose into carbon-12 or something else? Something else, and the reason is because its N to P ratio is way too high, and what's going to happen is beta emission. All right, we actually already calculated this. When carbon-14 undergoes beta emission, I think the product was a nitrogen atom, right? And I think that's kind of weird, because for a long time I just assumed that when carbon-14 decomposed, it decomposed into carbon-12. Like, isn't that kind of like a logical thing that someone would think, right? But when you look at it and you apply the idea of belt of stability and how we can get stable nuclei to have equal numbers of protons and neutrons, the only suitable decay mode is beta emission. And actually what is produced when carbon-14 decomposes is actually a nitrogen atom, so nitrogen 14, which I think is interesting, because for some reason I just assumed it would be carbon-12, but it's not. It decomposes into carbon, or nitrogen 17, or nitrogen 14. Okay, all right, so we'll stop here and then do like 13 minutes of review. So do grab that packet here. It's go.osu.edu 1220 Rev F. F stands for final. Or fun, I don't know. Okay, so let's grab this packet. Okay, where do we want to start? I know that the packet says Rev 4. I copied it. Sorry, this should say Rev F. Where do we want to start? The beginning? The beginning? Dang. Okay. Okay. All right, just to remind you what we talked about this term. We talked about solution chemistry. So that's chapter 13, chemical kinetics. Then we talked about chemical equilibrium for forever. Then we talked about like buffers, which was still part of chemical equilibria. Then we talked about entropy and Gibbs free energy, and then electrochemistry, and then nuclear chemistry. So not that many chapters in this class, but equilibrium was like a big, long, forever chapter. So let's go back to chapter 13. where we talked about dissolving stuff in water and the crazy amount of details that go along with that. So one of the things with solutions is we talked about saturated solutions and how we can communicate the maximum amount of stuff we can dissolve in a solution. So here, if I tell you the solubility of X, some salt, is 10 grams per 100 grams of water, what should happen if I combine 40 grams of solid and 100 grams of water and shake it about? What kind of solution should I get? Saturated, yes, saturated. It's very hard to make a supersaturated solution. To make this supersaturated, I would somehow have to trick or force this solution to dissolve all 40 grams, but that's never going to happen because a saturated solution is dictated by the solubility value right here, 10 per every 100. So this is saturated. What the picture will look like is something like this. Okay, we got 100 grams of water, all right? 10 grams of the solid is dissolved, it's aqueous, but then we would have a bunch of 30 grams of solid sunk at the bottom. That's what it's gonna look like. So if we add 5 more grams of solid, what's gonna happen? It's gonna sink to the bottom. Does the concentration change? No. Does the solubility change? No. It's just gonna sink to the bottom because we already reached our maximum. But what about heating the beaker? Will that make some changes? Yes, our intuition says, how does the amount of solid change at the bottom of the beaker? Decrease. Yeah, you're gonna dissolve more. But then therefore, where does the solid go? Into the solution. So the concentration of that 100 grams of water, is it gonna increase? It's gonna get more concentrated. Perfect. Okay. The reason this happens is because heating the beaker changes the solubility, increases the solubility, versus decreasing will decrease the solubility. So that's why the concentrations change. Okay, what about adding 100 grams of water? So let me take this picture. Tell me, how will this picture change if I change 100 grams to water, instead it's 200 grams of water? What's gonna happen? What's gonna happen to the solid? Some dissolves, yeah, so the amount of solid dissolves, it decreases. So does that mean that the concentration of the surrounding solution gets more concentrated, like in the previous? No, it doesn't, because here, now that I have 200 grams of water, the maximum I can dissolve is now 20 grams. But if we compare 20 grams over 200 grams of water to 10 grams over 100 grams of water, we see that, oh, those concentrations are actually the exact same. So I don't even have the answer here, because I put this together very last minute, is that there is actually no change. It stays the exact same. The only way we can actually change the solubility, the concentration, is by heating or cooling it. But here we can still dissolve more, but it's because we're adding more water to do the dissolving, all right? Okay, great. Okay. So let's talk about dissolving more stuff in water, why the idiom like dissolves like is kind of important, but really it's about matching intermolecular forces. In 1210, we talked about intermolecular forces in pure substances. Like if I just had a sample of sodium chloride, I would have dispersion, or LDF, but I would also have ionic bonding, because sodium is a cation, chloride is an anion. So full-blown charges attracted to one another. Or you can think lattice energy, keeping that together. Versus water has dispersion. It has, what else? Dipole, and H bonding. Very good. And H bonding. So those are in the pure phase. But when we make a mixture, what happens is that we mix our intermolecular forces. And depending on how attracted those solute and solvent particles are, will change the attractions or the enthalpy of mixing when we produce a solution. In general, when IMFs match or when IMFs are strong, things typically mix with one another. So when we look in the mixture, let's actually mix salt and water. We get NaCl aqueous. So if we just look at the pure forms, we see, oh, dispersion is present. That's a matching IMF. But is dispersion very strong? It is not very strong. So what's special about salts dissolving in water, it's not because of dispersion. That's the only matching IMF here. that dispersion is not the reason salt dissolves in water. It's actually the combination of ionic bonding and dipole-dipole. It's these two. I know they don't match, but when you bring those together, a special thing happens, and we call this ion-dipole interactions. And this is absurdly strong. This is very strong. Right? So this only happens for things that have permanent dipoles and salts, like NaCl in water. All right? So again, we're looking for strong matching IMFs, except for ion dipole, small caveat, but that's what we're looking for. All right? Okay, so let's look at this next one. The solute is NaCl again, so we have the same two pure IMFs, dispersion and ionic bonding. But here my solvent's different, it's not water, it's CCl4. So it has dispersion. Does it have anything else? Does not. It looks like methane, it's a nonpolar molecule. So you can see here, the only matching IMF is dispersion. Is ion dipole possible between salt and CCl4? Nope, there is no dipole in CCl4. So is this mixture likely to happen? It is not. It's not likely to make a mixture, so not likely to mix, because dispersion is the only IMF, and that's really weak. It's really weak, and I don't think it's strong enough to overcome ionic bonding that is in sodium chloride. That ionic bonding is so much stronger. Versus ionic and dipole-dipole create ion dipole that is able to break apart the hydrogen bonding in water. It is able to break apart the ionic bonding in NaCl, and that's because ion dipole is very, very strong. Okay, with all of those things in mind, let's talk about the energetics of dissolving stuff and how we observe it. In theory, we have solute and we have solvent. How we make a solution is we break apart all of the IMFs in the solute. That's what this red line is. And then we break apart all the water molecules. That's delta H solvent. So we break all of those apart. Then we bring them together and measure the attractions between solute and solvent. That's what delta H of mixing is. This, delta H of mixing, is the attractions between your solute and your solvent. So when this is strong, when your solute is very attracted to your solvent, you're going to have a big downward arrow because there's a large amount of attractions. Versus when you're only weakly attracted to your solute and solvent, delta H of mixings is going to be a lot smaller. Whoops. It's going to be a lot smaller because the attractions is weak. So here are the two different options we can have. We can break apart all our solute and solvent to some energy, but then we can get a lot of energy back by mixing them together. So what we see here, right here, this is delta H of solution. This is what we observe. So just based upon the arrow and the direction, this delta H of solution is what sign? Negative. So therefore the reaction is exothermic. So mixing this solution will what? Raise or lower the solution temperature? Raise it. Yes, exothermic reactions feel hot to us. They feel hot to us because the reaction's releasing energy. And it's because the mixture has very strong intermolecular forces. Delta H of mixing is a very large negative number. It's very, very strong. Versus, on the other hand, we have this type of mixing, where you break all the solute and the solvent, but you only get a little bit of attractions back. So we see that delta H of solution is a positive number. This is what kind of reaction? Endo. You mix this in water and the solution becomes colder, right? Why does this reaction happen at all? Entropy. Yes, it is entropy. Entropy is like these invisible fishing lines that are pulling this reaction forward, okay? Because in theory, we're making weaker bonds. That typically doesn't happen on its own. So the reason it happens is because of entropy. All right, and so positive delta H of solution, endothermic, because the IMFs in the mixture are weak. There we go. All right, so this is where I stopped in the last class, so I will stop here as well. So on Thursday will be our last class. We'll talk about bombs a little bit and then continue on with this packet.